Here a little bit, going back to step 5, when we go to succinyl-CoA to succinate, and addressing some of those pieces. Because I happen to remember that, if you remember last week, we went through, and the next few slides talk about, what the heck, come on pen, pyruvate and those conversions. Because what do we end up doing in the succinyl-CoA synthesis? Well, we put on a phosphate, and then we remove that phosphate with GDP. So it's doing 2 steps. And if we go back and look at our pyruvate, pyruvate did something similar. Okay, we did 1 step where we put on the phosphate, but then the very next step was we took the phosphate off. So in our pyruvate conversion from glycolysis, that process happened in 2 steps using 2 different enzymes. We have a kinase enzyme, and then we have the dehydrogenase. When we go back and look at step 5 in our conversion from succinyl-CoA to succinate, that conversion all happens with 1 enzyme. 1 enzyme is doing all that chemistry, okay, as opposed to 2. So that was one of the reasons why we had the 2 pyruvate slides pop up in the next sequence. It's just trying to get you to recognize we're doing effectively the same chemistry, but we're doing it all within 1 enzyme. The other thing that's an interesting feature is within this, we didn't need to bring in an electron mediator, like an ADH, an AD+. But then we had our step 6 and 7, going from succinate to malate. The succinate to fumarate is what? Kind of a reaction? What we're saying here, we did an elimination. Okay, I heard reduction. Is it a reduction? What is it? Because some eliminations aren't reductions. We did a lot of eliminations when we did an elimination when we went from citrate to acetate. Okay, that was an elimination. That was not a redox reaction. Is this one a redox reaction? What did we eliminate from the structure? We removed hydrogen. Okay. Did we remove H+, 2 H pluses? 1 H plus and 1 H minus. How do we know that? Well, if we get rid of 1 as H plus, what charge is on the carbon? A negative. To make the pi bond, I need a pair of electrons. Well, that negative supplies a pair of electrons. So if those electrons came in to make the pi bond, how did the other carbon-hydrogen bond break? The electrons would have to go out to the hydrogen, which means we have hydride. So we have loss of hydrogen in 2 places, which means, what was the loss of hydrogen? No, hydrolysis is the loss of water. And technically it's just the reaction of water. So we could call it that way. We could call it a dehydrogenation, I'll give you that.
That's the enzyme that's used, right?
We'll talk about that in a second too. Was it a reduction? What's the opposite of reduction? Let's try that.
Oxidation.
Oxidation. And to oxidize, what do you have to do? Okay, so we could do the lose electrons. How many electrons did you see in this? Okay, so that's a little bit challenging. Let's not look at the electrons. We talked about in organic chemistry, we had a shift in the definition. We don't have to go through and determine the actual oxidation states. We can increase the bonds to an electronegative atom and decrease the bonds to, what did we do in this reaction? Decrease the bonds to hydrogen. Did we do a reduction? No, we did an oxidation. Okay, and that's where this gets weird. Did you increase the bonds to oxygen?
No.
No, but you did decrease the bonds to hydrogen. Okay? So the rule for our oxidation from OChem isn't just oxygen, it's increase the bonds to a more electronegative element. Did we do that?
Kind of.
What do you mean, kind of?
Isn't carbon slightly more electronegative than hydrogen? But not.
Not really. I would say there's a larger effect here.
You added to resonance?
There's a resonance effect, which is one of the things that's driving this reaction. What can you tell me about that carbon versus that carbon? This is a hardcore OChem analysis.
Wait, oh, the two
The
green arrows?
two green arrows. We got left green arrow and right green arrow. What can you tell me about those carbons?
They're both alpha carbon.
Alpha carbon.
Yeah, they're both alpha carbons, but then there's no difference, so that doesn't help. I want to know something that's different about them.
Let's go back to the enolate.
Nope.
SP2 versus, SP2 versus SP3.
The one on the left is SP2, the one on the right is
SP3.
SP3. What is the difference between an SP2 and an SP3, Adam? Electronegativity. The more s orbital, or the less hybridized you are, the more electronegative the atom is. When we go to make that carbon double bonded, guess what we did? We increased the bonds to an electronegative atom. The sp2 carbon is more electronegative than the sp3. We did actually increase bonds to more electronegative. We did an oxidation. Okay? It's buried, but it's there. Yes, Terry?
So would you say that every time that you have an elimination reaction, it's an oxidation?
No.
It's oxidation.
It depends what you eliminate. So I can't draw the structure. Actually, I can draw the structure. Maybe. I don't know. We'll see. I think I can. What is that, Thomas? I think I can. Nobody? Thomas the train? Is that citrate? Did I get it? No, I don't think I did. Looks more like Thomas. I think citrate is this one.
Yeah.
Whoops. Because it's symmetric, it doesn't have a chiral atom. So there we go. That's citrate. Come on, give me that hydrogen. When we did the citrate to aconitate, what happened? We formed a pi bond. We formed the pi bond by getting rid of what? The OH and a hydrogen. We did an elimination reaction in that case. But in the process of doing that elimination, we don't do a redox reaction. Okay, because we lose oxygen and we lose hydrogen. Those are opposites each other when we're looking at the redox. Okay. I can't believe I drew the structure for citrate. Kind of happy about that. Sorry. Elimination, oxidation reaction, which means what do we need?
Is a mediator?
We need a redox mediator. So we're looking at our NAD plus or FAD. Okay. Fumarate to malate, what did we do? What changed? We go from fumarate to malate.
Add alcohol to it?
You did what with the alcohol?
Addition reaction.
Added, so we did an addition.
We have water,
Okay. We added the OH, but we also added
hydrogen.
hydrogen. So that was technically a hydrolysis. Water was used to cleave the pi bond. Right? Redox? No, because
Because they cancel each other out.
we increased oxygen, we increased hydrogen. They canceled each other. So it's not a redox reaction. Okay? So looking for those structural effects can help you identify where you've got different things happening, and you don't have to memorize quite as much, or your chemistry is a little on the weekend and you just have to memorize the whole thing. Okay? I would kind of recommend a blend of both. I think that's going to be the easiest approach. Make sense? Then in our last step, we go from malate to oxaloacetate. What changed?
Increased bonds to oxygen.
Increased bonds to oxygen, while at the same time decreasing hydrogen, which means we've got a redox, which means we need a redox mediator. There's our name. Okay? Kind of makes sense? Okay. Which is going to then take us into inhibition systems, I believe, on our next slide. Yeah. Okay. But before we get there, we've got a note at the bottom. This step is not inhibited by NADH, FEDH2, or ATP. Why did we have inhibition?
To stop, usually because we have too much of something.
We have too much of what, typically? Energy. So we're trying to shut down the citric acid cycle because it produces energy. Well, this step does what? Produces NADH, and NADH makes energy. So this would seem to be a good step to shut down, and yet it is not inhibited. Why? It's kind of a hard question, particularly because we haven't talked about all the inhibition stuff. The molecules in the citric acid cycle, are they only involved in the citric acid cycle? No. Those molecules could go out into the world and do some fun chemistry, right? Like make amino acids, be used in some kind of anabolic biosynthesis reaction, right? Why not shut down this reaction? Well, let's take a closer look. Come on, pen. A closer look right about, if my pen works, here. Does that look remotely familiar to anyone? You can say no, that's fine, not a big deal. How about if I turn it on its side?
Does it turn into a?
What is special about the carbonyl carbon right there? The purple dot? It is positively charged, which means if I say brought, I don't know, like a nitrogen,
Does it make the peptide bond?
I can replace that carbonyl with a nitrogen. Whoops. What happens if I somehow do that chemistry? And yes, I have to deal with that CO2 out there. But what happens if I replace that with a nitrogen? And then say run, I don't know, a reduction where I add hydrogen across that pi bond. What do I have? I need to add the other atoms. What am I starting to get darn close to? I actually did it backwards. I forgot about the carbon. So I highlighted the wrong piece. I didn't count my carbons right. Apologize for that. Oh, I did. Oh, yeah, I didn't count my carbons right. Talking about this piece, what does that look like to you? What functional group is the nitrogen? An amine. What functional group is that CO2? An acid. What do I have? I have an amino acid. Oxaloacetate can relatively quickly be converted into an amino acid. Which amino acid? Too bad Mark's not here with his list. I don't know which one it is either. I think it's aspartate. Okay, it's aspartic acid. Oxaloacetate is relatively very, very close to an amino acid. Do we need amino acids for anything?
Yeah.
Yeah, like making our peptides, making our proteins, which are enzymes, which conveniently are used in doing all of the citric acid cycle. Oxaloacetate is a very important intermediate molecule in the process of amino acid synthesis. So why do I limit or not limit this step? Well, can malate be converted across to the amino acid as quickly as the oxaloacetate? No, because hydroxide is not a good leaving group, okay, which means even if I brought in a nitrogen, it's not going to do that exchange very well, which means I can't place the nitrogen in there. I need the carbonyl chemistry to do the nitrogen exchange on. So malate, not as useful. Oxaloacetate, stupidly useful in other synthesis reactions. Right? So given the choice, yeah, I might produce a little bit more energy, but at the same time I create a very useful biosynthetic molecule, whereas the malate isn't so useful. Okay? So if I shut that down, yes, I don't have the energy glut, but I also can't do any real synthesis. Okay? Which is really what happens when we consider each of the inhibition steps and the control points, is it's not just the production of energy that we're concerned about, we're also concerned about each of those intermediate structures. Can those intermediate structures be used somewhere else? If they can be used somewhere else, I do want to shut down that control point because I don't want to get rid of it, I want to use that somewhere else. Okay? So our control points, energy-based and synthesis-based. Okay? The tricky part, good timing, Mark, jeez. We were just talking about you. It's okay. So we need to be looking at kind of both aspects. The energy-based one is easier to see because you're just looking at the citric acid cycle and you can see the energy production pretty much coming straight out of it. Okay? The biosynthesis becomes much more challenging. Remember that slide way back at the beginning of this where I said like this is all of biochemistry and we're just going to look at this one little section. We zoomed in and looked at little pieces. Okay? That's what we're thinking about when we're saying what points need to be controlled, because those control points are largely coming from the synthetic pathways of where else everything can go. Okay? Is that exceptionally challenging? Yes, that opens the door to a massive amount of chemistry, which is why the textbook kind of steps back from it and gives you real quick overview slides on looking at those synthetic pathways. Okay? So the big ones that you need to be aware of, okay, are the steps that require our NAD+, because that gets us our energy, and then the control points. Okay. Most of the control points are energy related. Notice that we have two other steps that aren't controlled by NADH. They are not control points. Why not? Well, fumarate, malate, oxaloacetate, pretty much everything on that bottom half or that second half gets us to oxaloacetate. Oxaloacetate is super useful synthetically. I want to make sure I can continue that out to produce oxaloacetate because oxaloacetate can then get used to make amino acids. Kind of makes sense? This does not say those other things can't get used. Those other things can get used, but oxaloacetate becomes more useful. Kind of makes sense?
You said the control points were energy-based and what else?
Synthesis-based. Okay. So if we look at the structures of compounds that are at our control points or around the control points, some of them are insanely synthetically useful, like alpha-ketoglutarate and oxaloacetate. Oxaloacetate's got a control point, okay, because that starts the citric acid cycle. Well, number one, I don't want to start it if I have tons of energy. So that's an energy control point. It's also a synthesis control point, because oxaloacetate is synthetically useful, citrate less so. Okay? So I want to control that first step because I get rid of a synthetically useful molecule and I produce energy. Okay? So once I've started that, I'm now committed to producing energy and I've lost my synthetic molecule. Once we've got through about half of it, well, now we want to get back up to our synthetically useful molecule because we could try and do biosynthesis with that. Kind of makes sense? Okay. Yep. So there are all our control points. We've got the on-ramp, the pyruvate dehydrogenase. Okay. We've got the citrate synthase, which is our step 1, the isocitrate dehydrogenase, and the alpha-ketoglutarate dehydrogenase. So lots of dehydrogenases. Your step 1, your on-ramp, that's the synthetic one, because we lose oxaloacetate. Okay. Step 3, step 4, and kind of our on-ramp are all energy-based. Kind of makes sense. So, cells and... I need to remember that I've got these questions already written, by the way, just for the record. Cells in a resting state. Oh, never mind. Ignore this one. That one's too hard. Because I keep screwing it up, so I'm just going to ignore that one. One of those reasons why I need to remember that I have these questions written. Provide a reasonable mechanism for the conversion of malate to oxaloacetate. Bit excessive, but looking at that, you should be able to describe what changed, okay, which we just walked through. So what you would have to be given would be our structures. Whoops. Okay, didn't do anything. So our malate, CO minus. Oh shoot, how many carbons do we have? Is it 4? And these hydrogens? I think so. Did I do that right for malate? This is, I don't remember them, so this is why I would give them to you. I think it's right. And since nobody's challenging me. So our malate to oxaloacetate. Okay. What I would do is give you the structures and then expect you to figure out what's going on. So what changed? And we could evaluate the mechanistic aspects to this just at a very, very simple level. What bonds need to break? The hydrogen-oxygen bond, which we'll go ahead and color purple. What else needs to break? The carbon-hydrogen bond. Which bond do you think is easier to break?
Carbon-oxygen.
Why is the oxygen-hydrogen bond easier to break than the carbon-hydrogen?
Differences in electronegativity.
Large difference in electronegativity. So that bond is going to be the easiest bond to break. So where would those electrons be predicted to go? Towards the oxygen or towards the hydrogen?
Oxygen.
Towards the oxygen. Right, if I want to make the pi bond, the electrons won't stop at the oxygen. Here we can do it this way. They won't stop there, but then they'll bounce into making a pi bond. Okay? Which then means the carbon-hydrogen bond has to break because we've exceeded the octet on the carbon. So where do the electrons in that carbon-hydrogen bond have to go? To the hydrogen. Meaning, what are we kicking out? hydride. Is that stable? No. So what do we need?
Mediator.
We need our mediator, NAD+, and there's not a shot in hell I can draw that structure. Well, let's see. There might be a mild shot in hell. There's our nitrogen. Ooh, I think I actually have it. The important part, at least. That hydride comes out, attacks there. Oh, look at that. Okay, that means that's got to go on the test. Just kidding. That's our, I think that's right. I could be wrong. I'm not positive about that part. Okay. But that's our reactive part of our NAD+. And the nitrogen was positively charged. The electrons come in and attack at that top position, which causes the electron shuttle around to pick up or make it neutral by putting the lone pair back on the nitrogen. Kind of makes sense? So recognizing where electrons have to shift around while getting it exactly correct isn't super important, but it is recognizing how bonds will break, and in that process, what does that mean you need to form? If you form hydride, well, that means you need a redox mediator. Okay? Why would you need a redox mediator with hydride?
Balance the charge.
Not even necessarily balancing the charge. It's to stabilize it. Hydride is insanely unstable. It's as small as we can get with a negative charge. Okay? Why use NAD plus instead of FAD? NAD plus was smaller than FAD. Okay? Why does that matter? I tried to make it more difficult by erasing the multiple choice. I like the stair part of that. I'm not sure I like the O chemistry. Sterics. Okay. FAD being a much larger molecule is going to be harder for it to freely move. Okay. NAD being slightly smaller is going to be easier to move around. Because it's easier to move around, we can then transfer that molecule to more places. Okay. It's a little bit more of a mobile redox mediator. The FAD, not so mobile. So if we go back, oxidizer versus reducer. No. How could I change the question to make that true? And we'll change it without dealing with the respectively part. So the oxidizer does not necessarily have to apply the NAD portion, and the reducer does not have to apply necessarily to the FAD. How could I change this so that that question becomes correct, or that answer becomes correct? There's two ways you could change it. The two ways both involve a particular atom. I maybe heard somebody mumble it. No. Hydrogen. What if this becomes NADH? Well, what does NADH have? Electrons on that hydride. So what could it do? It could donate that hydride, which is effectively losing electrons. The NADH would lose electrons in that process, meaning it was loss of electrons is oxidation. So NADH would be which molecule? An oxidizer or a reducer?
Does this go back to that?
Yeah, it's
So
back
a
to the
reducer?
agent. Yeah, so it's a reducer. It's causing something else to be reduced. Okay, so NADH would be our reducer. How else could we have changed it? Instead of making it NADH, we could have said, okay, I got one volunteer answer for FADH. And I think I heard somebody else mumble it in the back. FADH2. Remember, FAD picks up 2 hydrogens. Okay? So that's how we could change that question to make that first answer right. Yeah, there we go. Reducer versus oxidizer. Of course, I had to do it respectively when I wrote the stupid question. What a jerk. More mobile. I didn't say anything about sterics, but that was our whole steric argument. The larger the molecule, the less mobile it became. So NAD plus is more mobile than FAD. More stationary, which just happens to be the opposite of more mobile. Okay, so FAD is more stationary. Okay. Why is the conversion of malate to oxaloacetate not allosterically controlled? I don't have any multiple choice answers. Yeah, it's what we just talked about. In that discussion, we said that oxaloacetate is a biosynthetically useful molecule, okay, much more efficiently than malate. Because it is biosynthetically useful, we want to keep it for that biosynthesis. If we have enough energy to survive. If we don't have enough energy to survive, then we will sacrifice ourselves to exist.
So on that cycle, at the inhibition point, if we inhibited before we got to malate,
If we inhibited any one of those other X's within the cycle, like
Yeah.
over here.
so then, I guess the first one, we would then never make it to oxaloacetate.
Yeah, you're right. We would never make it to oxaloacetate. Okay? But in that case, that means we also don't have a glut of energy. So what might that suggest about the isocitrate or the alpha-ketoglutarate? Because if I inhibit at that first control point within the cycle, I end up with excess isocitrate.
So those can then be synthetically useful.
I don't want to just stall out with those reagents, so those reagents will then get used somewhere else. So isocitrate and alpha-ketoglutarate can be used somewhere else in biosynthesis. Okay. What happens if we don't get enough acetyl-CoA? Glycolysis for some reason shuts down. How can we respire? Respire. How do we still do breathing? Oxidative phosphorylation, that's the word I'm looking for. What's that? We could go to anaerobic, but that's suggesting that we had products from glycolysis. I'm saying glycolysis is gone. There's now no more glycolysis, which means no more pyruvate. How do we get energy? Break down the proteins into what? Into the individual pieces within the Krebs cycle. So we can sacrifice our own proteins and convert those proteins back into the intermediates within the Krebs cycle. Okay? So we don't have to go through glycolysis to make the Krebs cycle useful. We can generate those structures from our other proteins. Okay? And that kind of a process would be known as...
Is that the ketoacidosis? Or is it
quite possibly, but I want an easier word than that we've already talked about. No.
the cat breaking?
It would be catabolism. Okay. That was a little cat pushed in there. Hey, if it gets you to remember, I don't really care. I already look like a fool as it is. I'm not going to try and save myself. Okay. So, catabolism. We can do catabolism and break down other things to give us the intermediates. Once we have those intermediates, we can still produce energy. Right? What if we have tons of energy? And yeah, what if we have tons of energy?
Then when the cycle stop.
So we could stop the cycle, but then we've got those pieces still chilling around.
Change it to fat.
You could change those structures out into storage somewhere else. which could be fat, it could be more protein, it could be more muscle, it could be anything. So we want to be able to go out from the cycle as well, not just in. And if we go out from the cycle, we're now doing anabolism. Okay, so now if we get back down. So, catabolism, that's what this slide is showing, which is really what that second slide, or whatever slide it was in our slideshow way long time ago with that big massive spider network of all those little pieces. That's the gory version of what they're showing here. Right? They're centering in on the Krebs cycle, and they're saying, how can we make each of those pieces? Right? So let's say pyruvate. Yeah, we can do pyruvate. Carbohydrates, not a super big deal, because what is glucose? A carbohydrate. Okay, so we could go through and convert that down to pyruvate. That's kind of our standard glycolysis pathway. We could also take threonine. What's threonine? An amino acid, and we could convert that into pyruvate. Or alanine, okay? Or a myriad of other amino acids to make pyruvate. Right? What could we do with lipids? Well, lipids can be converted into fatty acids, which can then make it into our mitochondria, which can then go through a sequence of oxidation reactions to set us up with acetyl-CoA. Now that we've got acetyl-CoA and pyruvate, we can now start our cycle. Okay? So what they're just trying to show is how can we get those individual molecules from other pathways. There are those kind of steps. Okay? If you were to say get a more advanced degree in biochemistry, you would probably be looking at those more advanced steps and saying what is the gory detail happening behind each of those. Okay? Which nobody's doing. Good, because I don't want to talk about it. That's not quite true. If you're in a pre-health profession, they might actually go through and look at it, because if you wonder about diseases, well, diseases have some kind of physiological aspect tied back to something that's messed up within your biosynthesis pathway. So you may be looking at a disease and have to track back to, well, that disease is caused because you can't make oxaloacetate from aspartate, which now limits your ability to produce oxaloacetate, which then means you rely more heavily on other mechanisms to produce it. Well, if you rely heavily on those start to wear out, and that can cause problems, okay, within the rest of the system. Okay? So you're in a very careful balance between everything. So our big summary, all of our metabolic pathways are related. Metabolism, we can break things down to make our molecules for our citric acid cycle. The other option is that we could move to anabolism, and we can take those same molecules from our glycolysis, or from citric acid cycle, and push them outwards to synthesis of larger molecules. Okay, and that's what they're kind of showing that here, with really only one big thing. Alpha ketoglutarate can be used to make glutamate through a process known as transamination, which is really just a fancy way of saying turn the carbonyl into an amine. That's all that is. Oh, didn't we talk about that already with oxaloacetate? Yeah, oxaloacetate could be converted into aspartate. Why can alpha ketoglutarate be converted into glutamate then? What comes out at alpha ketoglutarate to succinyl-CoA? It's CO2. We lose a carbon. When we lose that carbon, what was our difference between glutamate and aspartate? It's one carbon. That's why when we do the transamination at those different points, we get different amino acids, because we've lost a CO2. Okay. We can look at the different pathways available to plants versus animals. So mammals can't convert acetyl-CoA out to those individual species, but plants can. mammals can really just do pyruvate to oxaloacetate. Why might that be an issue where plants need to do that and mammals don't? I'm just guessing. So. How do animals survive versus plants?
Take an oxygen.
Sure, they take in oxygen.
Animals eat.
Animals eat. Okay. Plants don't eat, which means the only things that they have to grow are the raw nutrients that they're feeding on. So to build larger structures, we want multiple pathways to spider out because, well, I start with basic elements. Okay, to build larger, I need to have as many different pathways so I can figure out and continue my synthesis process. Animals, why do we not need that process? Oh, I don't have it, so I'm going to eat a plant. The plant has it. Okay, so there's less of a evolutionary need to have that redundant pathway. That's, again, a guess, but, I mean, not a bad guess. So there's a pretty version of some of the anabolism. I thought there was a bigger one. Oh, because they're looking at different parts of it. So malate can go out. Interestingly enough, notice that they have malate going out instead of oxaloacetate. But what is malate going out to? Oxaloacetate. We have kind of a big issue within this that doesn't get discussed, I think, in the textbook, and I'm pretty sure it doesn't get discussed in the slides. Where is the Krebs cycle happening? In the mitochondria, which is the picture showing that pretty nicely. How many membranes are there in the mitochondria? There's 2 membranes. So to get your oxaloacetate, citrate, all of that stuff out into a system where it can actually be used, what has to happen? It has to transfer through 2 membranes. Well, how does it get through those membranes?
Gradients.
We could do concentration gradients. It's typically due to an active transport. Okay, that active transport needs to be fueled somehow. That's where we end up using ATP. So to get these reagents out, okay, it typically requires energy. This is why when they leave to make synthesis, it's because we have energy. That's the only reason they're leaving. If we didn't have energy, they stay inside to produce more energy. Okay? But once they're transferred out, that transfer mechanism usually centers on a couple different couples or coupling issues. So malate versus oxaloacetate can transfer across the membrane in a conversion process. As we transfer one across, we convert it across to oxaloacetate. Okay, so oxaloacetate is still our synthetically useful molecule. It's just how and where it is going in its synthesis process. Okay. Lipid anabolism. So now we're looking at how we can, and I don't know why they call this lipid because this isn't just producing lipids, but kind of beside the point. We can look at each of the things coming out of the structure or out of citric acid and what they end up being used towards or produced from. Right? Remember when we talked about oxaloacetate and I said, what did oxaloacetate look like? Almost immediately, what does it turn into? Aspartate through this weird thing called TA, transamination. Okay. So we're just looking at how those things can come out, what they end up doing in that process. Kind of makes sense? So it's neat. I do not expect the heavy details behind that, so please don't memorize all those. Okay? It's looking at how these things can be used. Okay? So as an exam question, I could say, what are the similarities between oxaloacetate and aspartate? Okay? And I might pick other structures and say, what is the similarities between these? Okay, as a short answer. Probably wouldn't make it a multiple choice, because that's going to be hard to do. Okay? Make sense? Not too much panic?
Would you give us the structures too?
I would give you structures, yes, absolutely. Okay, I do not expect you to memorize structures, so I will always give you structures. Okay? Structures and names. So the whole point of this was to generate NADH and FADH2, which are electron carriers. Okay? When we talked about the citric acid cycle, okay, we were calling it the aerobic respiration, and aerobic meant oxygen. Did we use oxygen at all in the citric acid cycle? So why is it the aerobic process? It produces these mediators, our redox mediators, FADH2 and NADH, and those then get used in a situation where they can react with oxygen. Okay? So the citric acid cycle is not the necessarily aerobic part. Okay? They generate those electron carriers. The electron carriers are what react with oxygen. Well, have we seen that yet? No. That's why we have the next chapter. Okay? Known as the electron transport and oxidative phosphorylation. Okay? Because what are we doing? Transporting electrons into a situation where we can use oxygen and phosphorylate. Okay? So that is typically referred to as ETC, or the electron transport chain, and then oxidative phosphorylation, which I think is kind of a misnomer, but we'll address that. So NADH and FADH2 end up getting used to transfer electrons around. Interestingly enough, they end up transferring their electrons to different enzymes, which then control how the electrons shift through the structure, and at the same time of transferring those electrons, they transfer H+ across a membrane. Okay? How the electrons bounce through those individual enzymes becomes a tricky bit of oxidation and reduction reactions. So for those of us that love oxidation and reduction, this could be really exciting. For those of us that don't, I would bet as most of the class, this would really suck. Okay? Which is why we don't go into it in a whole lot of detail, because I'm one of those people that doesn't. Okay? It does neat things. You go through all sorts of neat metal centers, and they know some of the mechanisms, but they don't know it all. Okay? So they're still actively working on it. The electron mediators end up getting converted across or exchanged to two new electron mediators, and that's coenzyme Q and cytochrome C. Okay? So our FAD and NH2, or FADH2 and NADH, transfer your electrons across to those new electron mediators and then shift things through the cycle. Okay? Why? Actually, it's not. I'm going to talk about that yet. Okay? So we generate our proton gradient, okay, which means the inner membrane space becomes insanely acidic. Okay? We need that extra membrane because if we didn't have it, we're now making our cells insanely acidic, and life as we know it would be significantly different because we'd be living in an insanely acidic environment, which changes all the intermolecular forces, and all of our proteins would have evolved to have been different structures. Okay? So because of that secondary membrane, we don't need to worry about that, okay? And we just have this really acidic section. Okay? We can use that imbalance because on the outside, or that inner membrane space, we're now generating what charge? A very strong positive charge. Does that show up? Yeah, it kind of shows up. Very strong positive charge in our inner membrane space. And then on the inner membrane, or our matrix, as they're calling it, what would then be building? A negative, because it's lost all of that positive. So we have a barrier between a positive and a negative. What is naturally going to happen? There's another place where we have lots of negative in this room. Where's that space? It's on the walls. All the electrical outlets. Okay? Those are all negative. What happens if you stick your finger in them? The electrons move through your body and to the ground to neutralize that charge. through what is effectively osmosis. It's just electrical osmosis. Okay? We're trying to neutralize that charge. So it is going to attempt to do that. As long as there's a barrier in the way, i.e. the plastic little plate that prevents us from sticking our finger into it, okay, it won't do that on its own. We have to mediate that somehow. That mediator is what biology has used to generate ATP. Okay, so we can control the flow, just like we control the flow by plugging in a plug to control the flow of electrons through that system. Okay. So, in our electron transport, we have a bunch of different complexes. Our super creativity in our names. Complex 1 followed by complex 3. That's interesting. Where's 2? Complex 2 is actually involved in the Krebs cycle. Complex 2, and I could be wrong on that one, but I think that's right, is our FADH2 carrier. Okay. So it is involved as kind of a secondary feature. It is not necessary for the electron transport chain because complex 1 can shuttle enough electrons into complex 3 that we don't need an extra one, but complex 2 will also supply electrons. Those electrons go through a similar process into complex 3. Okay. Complex 3 can then shuttle electrons over to complex 4, and in complex 4 is where we do the actual reduction. Is it reduction of oxygen to water? How do we know that? We added hydrogen to our oxygen. We decreased the bonds to oxygen, and now instead of having one bond to oxygen, I have no bonds to oxygen, and I've increased the bonds to hydrogen. Make sense? Okay, so that's our final kind of reduction step out there. Notice to do this, we have NADH come up with an H plus and dump in its electrons, okay, to produce NAD plus. At the same time that it dumps in those electrons, it shuttles across H plus. So we're now starting to generate that charge basis. Okay. Where do those electrons go? Well, the first thing they go to is FMN. What was FMN? As a hint, the M and the N are mononucleotide. What's the F? It's flavin mononucleotide. FMN is effectively FAD. Okay? It's a modified version of it. FAD was flavin adenosine dinucleotide. FMN is flavin mononucleotide, so we don't have the adenosine. Okay? FMN is a larger structure, which means it is bound within the membrane. It is not, or bound within the enzyme. It is not freely mobile. Okay? So, yeah, let's go ahead and continue with that. It can shuttle electrons then into an iron-sulfur cluster. So we have a bunch of iron and a bunch of sulfur all coordinated to each other, which are facilitating the electron transfer. Okay? That then transfers to another iron-sulfur cluster. That iron-sulfur cluster can transfer the electrons out onto CoQ. So CoQ then moves and transfers those electrons somewhere else. So CoQ is acting as an electron mediator. What did NADH act as? Why do I need another electron mediator? What do you mean the location? Yes. How is that going to be an issue? Size, possibly. I would argue there's something better. Hydrophobic versus hydrophilic forces. NAD plus is much more hydrophilic, so it's going to be found in the cytosol or in our free membrane or outside our membrane. CoQ is being transferred through the membrane, so it's going to be much more hydrophobic than, say, NADH? Why would I want my electrons being transferred through the membrane and not through the outside? Say that. That's a.
So they don't get absorbed.
If we had our electrons floating free will on the outside, that could potentially mean we're dumping electrons off where we don't want them to be. Like if we just had bare open wires for our electrical outlets. Okay? Generally not a good idea. When working with those, we put on insulating materials to prevent that electrical shock. So the same idea is happening here. CoQ is going through the membrane to kind of nullify that effect. Okay? What might that suggest about the reactivity of CoQ versus NADH? Less reactive? CoQ can only be found in the membrane. NADH can be found everywhere. CoQ is probably actually more reactive because it's bound within the membrane. The membranes are insulating material. It protects it. It's effectively the coating on our wires. NADH is where it can now actually move around. So I would bet CoQ is actually going to be a little bit more reactive and freewheeling with the electron density. Okay. It can then move up to complex 3. CoQ will dump electrons into complex 3, again through a variety of nasty complex processes. We have another iron-sulfur cluster. We have cytochrome B. Okay. In all of those electron transfers, we're going to end up shuttling, again, hydrogens across the membrane. And at the same time, we're going to dump those electrons out onto cytochrome C. Cytochrome C is found outside the membrane. Okay, so it's probably a little bit more hydrophilic. Why is that going to become potentially a problem? Cytochrome C could potentially float off just like NADH and prevent our cycle from functioning. Cytochrome C is pretty closely held to the membrane, because we want these processes to happen relatively quickly and not go anywhere else. So while it is not membrane bound, it's going to be hovering pretty close. Cytochrome C can then shuttle those electrons into complex 4 for our last and final stage where we can do the full reduction out into water. Why not do the reduction to water at the very beginning? There's a couple thoughts that could go with this.
Because you're going into a hydrophobic area, so the water would kind of inhibit that.
Well, so really what I'm saying is why not out over here we do, whoops, that's supposed to be oxygen to H2O. Why have complex 1 and complex 3? Why not just shuttle electrons immediately in and spit out? So there's one thought. The whole point of this was to generate a bunch of positive charge on one side and a bunch of negative charge on the other. If we did it in just one step, how many hydrogens do we get? We only get 2 hydrogens. Yes, that generates a partial charge, but it's not a large charge differential. If we tie the electron transfer back to those other mechanisms or other complexes, instead of generating just 2 hydrogens across the membrane, I now have a proton gradient of 10. Okay? 10 positives lost from one side. That's going to generate a larger gradient, which means more energy potentially coming from it. Okay? Another reason. Potentially a harder one. You've seen like power stations around, right? Would you ever just plug in directly into a power station? Why not? There's too much power coming out immediately. Those power stations will transfer very high energy power into a transformer, which drops the power down to a reasonable level. If we take the energy from our NADH and directly dump that into a reduction, we're probably generating an overpotential that is actually going to release too much energy. We want to control that energy release so that we don't get that much of an overpotential. Okay? which is fun because then what we're looking at is ultimately our redox reactions and cell potentials for each of those steps, which I think is the next slide. No, I'm slightly different formatted version of it. We'll be there in just a second. Looking at NADH, dumping it into FMN. Notice the FADH2 in blue. See that there? Where is it? Guess what FADH2 is? It's complex 2. FADH2 is dumping electrons into CoQ. Okay? It's not FADH2 just free floating. That's complex 2, and the electron carrier from complex 2 is FADH2. Okay? So it's dumping electrons from FADH2 into CoQ. CoQ can then dump those electrons out into complex 3, which is red, cytochrome 1 or cytochrome B. Why are they showing two different things? If we go back to complex 3 has two different cycles happening with it. Okay? One shuttling electrons directly across so that we can get them ultimately out to complex 4 through cytochrome C. Another set in what is known as the Q cycle, cytochrome B, which is to refresh CoQ, okay, so that it can be used again. Okay. That makes it out to cytochrome C. Cytochrome C can then dump that into complex 4. That's our O2 producing, or O2 consumer. Okay. Complex 2, and this is the one in blue, FADH2. Okay. FADH2 is not complex 2, it's the redox mediator from complex 2. Okay. Which does show up later in the slides. I thought I had it show up earlier, but I was wrong. Okay. Which then means we get to the fun part, and by fun part, see this is why prerequisites for this course are just freaking weird. Because we look at this and we see cell potentials. Several of you only took 130 and 230, didn't go through the 152. Anybody recognize E? For those of you that took that class? Yeah, you don't, because it's never discussed in 130 or 230. Okay, what is E for those of you that went through more chemistry? It's not energy. It's a voltage. It's the cell potential. It's looking at the ability for that reaction to produce electron current. Okay? When we look at our voltage, that is similar to, because it's an energy, it's a different form of energy. Okay? So it is similar to what we've talked about before, Gibbs free energy. And in Gibbs free energy, what was a good change in Gibbs free energy? What did I want it to be? Negative. Okay? That was a spontaneous reaction, was a negative delta G. Okay? What is a good delta E? E is an elephant. We want it to be positive. Seriously, why? Why is it all of a sudden now supposed to be positive and not negative like delta G? Scientists defining terms from different fields. This is now a crossover of electrochemistry with physical chemistry. Those two concepts of energy measurement were developed independently, and then somebody went, oh crap, they're both energy, they need to be related to each other. And instead of one saying, okay, I understand why you're saying it's negative, I'm going to switch mine to now be negative, we instead come up with a conversion factor, which is then expressed at the bottom. And when we look at our G's, okay, there should be deltas in there, but we're getting issues with my typefacing. Your delta G is equal to negative R. R is the, everybody should have seen that potentially. Is it constant? What constant? R is the gas constant, okay, which is a bit bizarre because we aren't really looking at gases, but it is officially the gas constant with different units, times T, which is our temperature in what unit?
Kelvin.
Has to be in Kelvin. Why Kelvin? What's the issue with degrees Celsius and Fahrenheit? They have negatives. As soon as they bring in a negative, that messes with all the sign changes on this, and that just turns it into a complete mess. Okay, so your temperature must be in kelvins. And then our relationship is the natural log, okay, which is awesome. Everybody loves a log, times the change in the cell potential E. So if I have a negative delta G and I have a positive delta E, well, they have to be referring to the same thing. How do we make sure they refer to the same thing? That's why this minus is here. Okay, I'm like 90% positive that that is why we don't reference them both as negative or both as positive. We had two systems that did not agree with each other, and so they developed a system that they could mutually agree to saying, we'll just incorporate a minus sign in our conversion. Just change how we perceive either one of them so that the sign is always the same, because then you don't need an extra minus sign. Didn't happen, so this is what we deal with. Okay? So what we're looking at is all of those cell potentials. You may look at that, God, that looks like a mess. Yeah, it does. What are all those cell potentials referring to? Well, what's happening up at the top? Okay. That's our water reduction. Okay. To get that reaction to work, we have to couple that with other reactions. Or other electron transfer processes. So it's a question of how do we stack these so that our overall cell potential is positive. Okay? The water reduction is one that's relatively easily positive, so that can make it pretty simple. And it's now just a question of how do we very carefully control the electron flow at each of those other cases to make sure that we can get more protons across our gradient to generate a stronger battery. Okay? And it's not necessarily for the reduction, it's so that we have that stronger partial charge differential, which we use later on. Okay? So if we took a look at, what's our question? 2 electron carriers, NADH coenzyme Q. NADH to coenzyme Q or coenzyme Q to NAD+. So let's take a look at those. I gotta find them. Oh my gosh, we gotta find them in this. Yeah, there's CoQ. Good call. Let's look at that one. And would I expect electrons to be transferred to NAD+ from CoQ or from NADH to CoQ? How would I go through and set this up? Let's see if I can do this. Can I just run the reactions as is? Why not? I like your head shaking, Lauren. Why not? Where are the electrons? Where are the electrons? They're both on the reactant side. Meaning for those reactions to run together, they both must consume 4 electrons. Where did I get electrons from? Oh, that's right. I didn't. Okay. So if we're going to couple these reactions, the electrons cannot be produced nor consumed. So I have to go through and flip these reactions in such a way that the electrons balance out. Okay, so let's say I have CoQ emit electrons to NAD+. Oh, and I forgot the 2H+. Right? So now CoQ loses 2 electrons, and NAD+ accepts those 2 electrons. Everybody kind of see that? Okay. Is that going to be a functioning reaction? Okay. For it to be a functioning reaction, we have to evaluate the cell potential. The cell potential needs to be what? Positive or negative? Positive. Okay. Well, NAD+ I did not flip, so its cell potential stays the same. But I did flip CoQ. So CoQ's cell potential needs to become negative, just like if it was an energy. I can then add those cell potentials. When I add those cell potentials, what do I get? A negative value. Does that reaction work? No, because I get a negative cell potential. So CoQ-H2 cannot shuttle electrons to NAD+. Okay? Which is good because how does it work?
We get it from
NAD8 or NADH shuttles the electrons to CoQ. We run the reverse reaction. And if we run the reverse reaction, you should notice that we get a positive cell potential. Okay? Kind of makes sense? So it's a question of adding or subtracting reactions, much the same as we did with the Gibbs free energy back in Unit 1, and I think maybe even again in Unit 2. Okay? But now we're doing it with cell potentials. Okay? Electron transport, that says we're done, aren't we? My clock says I got a minute. Complex 1. Okay, and I'm not going to get into it in too much. Complex 1 is our NADH CoQ oxidoreductase, which is fun. Why do we call it oxidoreductase? Oxido sounds like oxidation. Reductase sounds like reduction. So in this process, we're doing an oxidation and reduction. Well, that would then be nothing. So why are we talking about breaking it into an oxidoreductase? Why are we mentioning both? Depending on our frame of reference, whether we're looking at NADH or CoQ, we're looking at an oxidation or a reduction. Okay? So they're mentioning both because it is an oxidation-reduction reaction. Okay? It's just a question of where those pieces then go. Okay? So that's all they're trying to address there. So your electrons, as we talked about, go from NADH to FMN. There's our structure for FMN. Notice it is effectively the same thing as FAD. It has the reactive part. The reactive part, which that is this unit, by the way, way back when, the very beginning of this unit, is recognizing where we can add electrons to FMN. Anybody remember? Because you started to review already. To the nitrogen. This nitrogen? No. No. Good answer. This one? Yes. 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 That is where you can put them.
That one and then the top one?
You can put electrons here. I should be doing these as single arrows. Which then means you can put another one up here. Okay. So you can get both of those hydrogens being added. You can do it in single fashion, single electron transfers or double electron transfer. Okay. Those electrons then get shuttled through complex 1, and that's what they're trying to show at that bottom, looking at how all the electrons then get shuttled out from one place to another, to another, to another, ultimately going into CoQ to make CoQ-H2. CoQ-H2 is now our electron mediator, which can float off to complex 3. And of course, the next slide will be complex 2. Son of a...